Hey everybody. The video for today is a supplement on bootstrapping. I know I've gotten quite a few questions about bootstrapping and kind of how to use Excel and what the idea of bootstrapping is, and I wanted to cover that in a supplement today. So first I want to talk about what is the basic idea of bootstrapping, where would we use it, why would we use it, and how is it used? And then I want to look at a couple of Excel demonstrations, and then finally just kind of go through a couple of the MyStatLab problems just to see how to work through those with the actual data, how to get it into Excel, work with the data, and all of that. So we'll start with the basic idea. So the idea of bootstrapping is to get a confidence interval for, I'll just say, for instance, maybe for the mean. And we have a couple of ways of getting confidence intervals for the mean, right? We have a z interval for the mean or a t interval for the mean, but the problem is that both of those come with some assumptions. Either, for instance, the assumption of normality of the population or n bigger than or equal to 30. We could think of a scenario where we might have a small sample size, and where upon investigating that sample, we don't really think it comes from a normal distribution. So we really can't comfortably use those confidence intervals we've developed. So what if the assumptions are not met? Or we could say the same thing for proportion, right? We said for confidence interval proportions, we need 5 successes and 5 failures in our sample. Maybe our sample doesn't have that. What if we want to develop a confidence interval for a proportion and that assumption is not met? Or same thing with confidence interval for variance and standard deviation. What if the assumption of underlying normality is not met there? How would we develop such a confidence interval? So we have some confidence intervals we've come up with formulas for, but those formulas rely on assumptions. If the assumptions aren't met, we don't really want to use those formulas because they might give us a result that is not what we think that we're actually getting. So we might be claiming, say, a 95% confidence interval, but maybe we're only actually getting 90% confidence, for instance. The other reason we might want to use a bootstrapped confidence interval is if we want a confidence interval for, let's say, the median. Well, we don't really know much about the sampling distribution for the median. It doesn't have like a central limit theorem that comes along with it. And so if we don't really have any formulas to work off of, we need some other approach, some other way of getting a confidence interval. Or we could even say, if we remember that S squared is a good estimator of sigma squared, but really technically speaking, S is not a good estimator of sigma. We kind of took it as a rule of thumb and kind of pretended that it was and said, it's probably good enough for our purposes. But if we wanted to be precise, the formulas that we developed with the chi-squared distribution and so on for sigma squared, for confidence interval for sigma squared, they don't technically apply to sigma. So how could we get a confidence interval for sigma if we were worrying about that technicality? Or we could imagine that there are many other sample statistics that we've talked about that we maybe don't know the sampling distribution of. So in all of these cases, we don't have a nice, closed form formula where we satisfy all of the assumptions that we can use to compute a confidence interval. So here's the general idea of bootstrapping a confidence interval. So say we have a population and we take a sample. So maybe we'll call this sample 1. And from that sample, again, let's just go back and center our discussion around getting a confidence interval for mu, but you could replace mu with any of these other parameters, and the process would be the same. So I have my population, I take a sample, sample 1, and from that sample, I'm going to compute X bar, and I'm going to call this X bar 1. So this is the sample mean for sample 1 for this subset of the population. Now, I imagine this random process, the randomness is coming in here where I take the sample, is something like, let's say, rolling a die, right? If I have a 6-sided die, and I'm not really sure whether it's fair or not, one thing I could do is I could roll it a whole bunch of times and just, for instance, look at the percentage of time that, say, 1 comes up or a 5 comes up. So the randomness is from taking a sample. So I could just take a sample from the population a whole bunch of times. And let's say that n equals 50 or something like that. I don't know. Or no, let's say n equals 20 because I was saying that we didn't satisfy the assumptions. We want to use the same size sample every time so that in that sense, it's kind of like if we were rolling a die, we'll be rolling the same die every time that we're generating the data from. So I generate sample 2. That's kind of like a second roll of the die, a second empirical estimate for mu. And from there, I can calculate X bar 2. I can take sample 3. And these are, of course, just graphical, like abstract depictions of the samples. We wouldn't want to take samples actually in clusters like this. And I could imagine these, again, as being something like, 3 rolls of a die that I'm curious about. And I could actually do this a whole bunch of times, right? I could do this maybe 1,000 times. And each of these X bars is kind of an estimate of mu. And now I have something like 1,000 estimates of mu, right? Or another way of looking at it is each of these X bars comes from the distribution of X bar, the random variable. So X bar 1 is one observation of X bar, the random variable. X bar 2 is another observation from that random variable, and so on. I now have lots of observations from this random variable X bar. In other words, this list of numbers here, X bar 1 through X bar 1,000, in and of itself represents a data set. And what it does is it gives me an idea of the empirical distribution of the random variable X bar, in whatever situation I'm in. Say, for instance, with a sample size of 20 and in a population that's, say, not normally distributed. So this gives me an empirical distribution of the random variable X bar. Now, again, if I have those assumptions met and I can use my central limit theorem, I can use the conclusion of the central limit theorem to say an awful lot about the distribution of X bar. But if I don't have access to that, maybe my assumptions aren't met, or maybe in a different context, I don't have something like the central limit theorem to apply to the statistic I'm interested in, then it can be very valuable to get this empirical distribution to, in a sense, roll this die 100, 1,000, 10,000 times and get a bunch of information about the thing that I'm interested in. Now, if I think of this as an empirical distribution of X bar, then what I could do here is if I wanted, say, a 95% confidence interval for mu, well, I could just take this data set and I could say, well, I want the error to be split evenly between the two tails. So that's a lower bound that's at the 2.5 percentile. And an upper bound that's at the 97.5 percentile. We know how to compute percentiles for data sets. We did that in chapter 3. So I just take this data set, X bar 1 through X bar 1,000, this set of 1,000 numbers. I sort them in increasing order. I go through and I find the bin that has the 2.5 percentile in its bin. I pull that data value, that's the lower bound of my confidence interval. And I do the same thing with the 97.5 percentile. I find that data value, and that is the upper bound. And this is my confidence interval then. The LU that I found up here would be my empirically derived 95% confidence interval from U. I didn't have to use any formulas. The only thing I needed to do is be able to compute my sample statistic. If I was able to compute my sample statistic, I can find the confidence interval that I'm interested in. I didn't need to know formulas or margins of error or z-scores or t index values, anything like that. I just needed to be able to compute X bar a whole bunch of times and then crunch the numbers to find percentiles. So this is the big idea of bootstrapping. Now you probably say to yourself, well, this is kind of a silly idea though. Why is it a silly idea? Well, what's the whole reason I'm dealing with samples instead of populations? Well, because dealing with populations requires me to take a lot of time and effort and money and so on and get cooperation and everything. And that's just not feasible. So if it's not feasible to sample the whole population, is it really feasible to take 1,000 or 10,000 separate samples from the population? Probably not. So, I mean, this seems like you might say, okay, this is a good idea in theory, but, you know, I mean, it's an interesting idea, but it's a moot point because we could never do it. But here's really the magic of bootstrap resampling and why it's called bootstrapping. It's there's a saying, picking yourself up by your own bootstraps, like reaching down, grabbing your shoelaces and pulling, and somehow that's supposed to pick you up off the ground. It's something that seems like an impossible task. But it turns out that there's a way that we can simulate these samples. So let's forget about samples 2 through 1,000. And let's suppose we just have sample 1 that's whatever of size 20. So I have sample 1. I'm going to keep calling it sample 1, but this would be the only sample that we're dealing with. So this is kind of the theoretical idea up here, taking a whole bunch of different samples, but we're shifting gears now. We have sample 1 that's the actual sample. This is the actual data set that we went out into the population. We made measurements, we collected it. Here's our data. That's what it is. What I'm going to do is I'm going to, and let's say this is of size 20, I'm going to do something called a bootstrap resample. In other words, I can think of sample 1. I could think of using it to derive X bar 1, say one data point about the distribution of the random variable X bar. But really, sample 1 has quite a bit more information than that, right? X bar 1 is a descriptive statistic of sample 1. Sample 1 kind of contains a lot more information. It has lots of data points in it. Well, sample 1 I could actually think of as kind of an estimate of the population frequency distribution. In other words, in a sense, it kind of looks like just a miniature version of the population. Of course, this presumes that we took a good sample. We don't have bias introduced in the sample, right? We took a good random sample and so on. But if I have, you know, 1 million people, and I think that, you know, this percentage of those 1 million people have height between 5 feet and 5'6", and this percentage between 5'6" and 6 feet, and this percentage between 6 feet and 6'6", and so on. If I take a sample, random sample that's, you know, of a reasonable size from the population, I'd expect that those percentages would roughly remain constant. Kind of going the other direction is what we call the law of large numbers. So I expect that the sample, the frequency distribution is going to look kind of like the population frequency distribution, at least in relative terms, in percentage terms. The sample should just look, in theory, like a microcosm of the population. So what I would love to do is just to draw from the population, say 1,000 or 10,000 times. But what I could do instead is maybe draw from my original sample. I want to draw a sample of size 20 from sample 1. Now, of course, if I did this without replacement, I would just get a whole bunch of copies of sample 1. That's not really super helpful. But what I want to do is I want to take a sample or samples of size 20 from sample 1 with replacement. So maybe the first data value or the value of the first data point gets chosen 3 times for this new sample, and maybe the second data point doesn't get chosen at all, the third data point gets chosen once, the fourth data point gets chosen twice, right? We're picking different data points from sample 1 at different frequencies in this resample. So it's theoretically possible that this resample ends up just looking like sample 1. Maybe just by chance we picked x1 once and x2 once and so on out to x20 once. But most likely we're going to get some shuffling around. We're going to pick some of these data points more often and some less often than others. So when we do this, we call this a resample. And I'll call this resample 1. So resample 1 is what's kind of taking the place of this first bit over here. I could do this again, right? I could do the same process. I could randomly choose a sample of size 20 from sample 1 with replacement, and that gives me resample 2. I could do it again and get resample 3 and so on, down to say resample 1,000 or 10,000 or something like that. Typically, we want a large number of samples or of resamples because we're trying to fill in a distribution here to get a good idea of the empirical distribution, and particularly the tails, which is where we're often looking for these lower and upper bounds, is starting to get into the tails. We typically want a pretty large number of samples, or in this case, resamples. And then I can do the same process. I can compute x bar 1 from resample 1, x bar 2 from resample 2, and so on, down to x bar 1,000. I can look at this as my data set. I can find L and U as, for instance, the 2.5 to 97.5 percentile of this data set, and get my confidence interval. Now, where's the magic here? Why does this save time? Well, it's because this step is cheap. Right? Generating a resample is cheap. Generating a brand new sample is expensive. But generating a resample, I just basically tell Excel or Python or some programming language, hey, I want you to draw a random sample of size 20 from sample 1 with replacement, maybe half a dozen or a dozen lines of code. And you tell it, I want you to do this 1,000 times. And by the time that your finger is done pressing the enter key, it's already got your resamples, your X bar 1 through X bar 1,000, and your lower and upper bound already computed. So because the speed of computers these days, the computing power that we all have in our pockets, let alone on our desktops, this is a very cheap process. Now, 100 years ago, this wouldn't have been nearly as cheap of a process. But today, very cheap process. Okay, so that is the idea of bootstrap resampling. One detail is this does seem kind of hand wavy. Like, does this actually do anything? Is this actually a valid thing to do? And the short answer is that yes, people have done all of the mathematics, all of the theoretical background to show that this actually is a reasonable thing to do. So I mean, I've given kind of an argument as to why maybe it ought to work, even though at first glance it seems like it shouldn't work. But you do want to make sure that the thing actually works and the math holds up and all that. And people have done that work and have verified that this process does do what it's saying that it does. Okay, so let's look at a couple of demos. My Excel is probably going to run a little bit slowly because there's just a lot of data to deal with, and Excel doesn't handle lots of data super well. Okay, so here is an example where we have a sample of size 10. Here we're coming from an exponential distribution, so a distribution that is skewed right, that's decidedly not normal. Oh, and I said n equals 5 here, this should say n equals 10. And the exponential distribution has a parameter, and this is what I chose the parameter to be, 1 over 2,000. And for the exponential distribution, that means that the true mean we know is 2,000. Because I know what the distribution is, I'm using this as a demo. I know what the true mean should be, 2,000. So then I can evaluate if I have a confidence interval from mu, say, I can know whether my confidence interval covers the true mean or not, because in this case, I do know what the true mean is. Now, of course, typically I wouldn't know this information. That's the reason I'm taking a sample, is to find out something about my population. But in this case, for the demo, I do know this, so I can check and see if my bootstrapping method does seem to be working. And then what I do is I take bootstrap resample. So here's resample 1. The Excel code's a little bit complicated to kind of understand what it's doing, but essentially it's just drawing a sample of size 10 from this original sample up here with replacement. So for instance, you see 477 got chosen 3 times, and you see, for instance, let's see, who didn't get chosen at all? The 2578. Yeah, it looks like in sample 1, data point 3 with value 2578 looks like did not get chosen at all. So some data points are going to get chosen more than once, some are going to get chosen no times, and this was what our first resampling happened to be. Now I computed 100 bootstrap resamples. Typically you'd want to use 1,000, 10,000, something like that, but Excel bogs down pretty quickly. So we'd use something a little more powerful, maybe something like Python or R, that's a little more designed for crunching large amounts of data. For each of these resamples, I can compute X bar. So here's my resample. Here's X bar for that resample. Here's another X bar and another. These are like my X bar 1, X bar 2, X bar 3. These are empirical, this list, this data set fleshes out an empirical estimate of the distribution of X bar. And then what I would do if I was, say, doing this more by hand, I would take these data, I would sort them lowest to highest. I'd say, okay, there's 100 of them. If I want, for instance, the 95% confidence interval, the 2.5 percentile, well, I'm going to go from my first data point of 100 data points is going to go from 0 to 1%. Second data point is from 1 to 2%. Third data point is 2 to 3%. So the third lowest valued data point is the one that I would take as my lower bound for the 95% confidence interval. And then by symmetry, my third highest valued data point would be the upper bound. Cool. So if we do that for this X bar, my 95% bootstrapped confidence interval for mu ends up being this, 946 to 2097. And we see that does actually cover the true mean 2000. If I recompute this, so I'll recompute it 20 times, and we'll see we'd expect it to miss 1 or 2 times. And I'm just focusing on the confidence interval for mu. Now I have a couple other things on here as well, but for right now, just thinking about mu. So we missed that one. So there's 10, we missed 1 out of 10. We got a pretty good run there, 19 in a row. And there's number 23 missed again. So, right, so it does seem that we missed, actually the first try we missed, we got 21 more in a row that we succeeded in covering mu, and then we missed again. So, I mean, something like 1 in 20 does seem pretty reasonable for this, right? We succeeded in covering mu, seemingly in the ballpark of 95% of the time. Or we failed to cover mu, something in the ballpark of like 1 out of 20 times. So the standard deviation also is 2000. So we can do a similar thing for the standard deviation, right? I can take each of these bootstrap resamples. I know for the confidence interval for standard deviation, or for variance of standard deviation, I definitely need normality to use the chi-square distribution and all those formulas. But here I can just do the same process. I don't need to know anything different to compute a confidence interval for sigma than I needed to know for mu. I just need to know how to compute my point estimate. Well, to compute my point estimate. Sorry, I hit escape and it messed up Zoom instead of escaping out of Excel. But there we go. If I can compute my sample statistic, my point estimate, that's all I need to be able to do. And I get a 95% confidence interval for sigma. And again, this one happens to have missed. But if we check, say, the next 20, let's see how many times we miss. So we missed. So it seems like we missed 3 or 4 out of 10. So it seems like we're missing a lot more with sigma than with mu. And that is one of the downsides of something like this, is these bounds, can be a little bit tricky. This process works very nicely for mu. We see it's not working, so great for sigma. It's not working as well as we'd expect from sigma. Kind of like with any empirical method, there are going to be other complexities that come into play that we're really not going to get into, but we see that the confidence interval for sigma seems to fail a lot more than it ought to, even though the one for mu worked quite well. We can also look at the median, right? We didn't have any formulas that we developed for the median. We don't have a good like central limit theorem equivalent or something like that for the median. But we can do the same thing. We can compute the sample median, develop a confidence interval in the same way as the others. As long as I can compute the sample statistic, I can crunch these numbers. And let's check this one. So it seems like I always fail on the first try. I don't know. So there's 1 failure out of 10. 1 out of 20. 1 out of 30. I mean, you can see that it seems to be successful in maintaining that 95% confidence level. I don't know why it like failed on the first one for like everything that I tried, but even for mu, it failed on the first one and then it succeeded for the next 20 or 21 or so. It's just a little bit funny. But yeah, so this is our this is a demo for a bootstrap resample for a sample of size 10 with an underlying distribution that is skewed right. If we had an underlying normal distribution, so if we took a normal with mean 100, standard deviation 15, again, sample size 10, and did something similar. So here, because the underlying distribution is normal, we can say exactly what the confidence intervals ought to be, right? We can use our formulas to get a confidence interval for mu, where we compute what it actually is, and a confidence interval for sigma, again, where we compute what it actually is. And then we can look at the bootstrapped intervals And we can try to figure out, is there agreement between what the actual confidence interval is by calculation, by theory, versus the empirical one through bootstrapping. And again, if we look at mu, we get a pretty nice error rate. So about 3% error in the upper and lower bounds. And if I recalculated it, all of these are randomly chosen. These are randomly, each one of these is a new random draw of 10 numbers from a normal distribution and so on. Each of these is randomly sampled. So I'm not, cherry picking the numbers here or anything, but if we recalculate over and over with completely new random draws each time, you can see that these error bounds are staying pretty low. And of course, I stopped at one, probably the worst one so far with 7% error on the lower bound, but you can see they're typically in the ballpark of 1 to 2% difference between the computed errors or the computed confidence intervals and the bootstrapped ones. You'll notice the confidence interval for sigma doesn't work nearly as nicely, right? Much bigger error there. And again, this could have, there could be several contributing factors to this, not the least of which is that S is actually not a quote good estimator of sigma for some reasons that we briefly discussed earlier. So that is the demo, just kind of showing you, hopefully that convinces you that bootstrapping works, at least in some scenarios, reasonably well. Okay, so I have this second Excel spreadsheet to show you. This is a spreadsheet that I put together to maybe help you out a little bit with the MyStatLab homework and to experiment a little bit. So this is an example of an original data set of size 4. We're going to be using 200 resamples here just because that was the number used in one of the MyStatLab problems. And here we have different resamples. So here I've actually done random resampling, but you could, just choose a certain resampling and put it in here. And we see there are 200 resamples. So number of resamples is 200. And then these cells, lower bound and upper bound, give you L and U for the confidence interval. The 2.5 to 97th percentiles, remember the numbers that we are interested in finding to give us the lower and upper bound for our 95% confidence interval. It turns out that for those percentiles for 200 resamples, those are going to fall right on the border of kind of two like percentile bins. And that's what goes in A and B here. So in other words, this would be saying, okay, find the 20th smallest value in this list over here and the 21st smallest value, and then average those two together. So in this case, it's averaging, I guess, these two numbers together. Now, these yellow cells here and here, you're going to have to enter formulas or numbers in here. So I'm not just, handing you the answer to the problem, but this should give you a pretty good start for the problem. So this first sample mean cell should compute the sample mean of this first resampling. So you want to type a formula in here that computes the mean of these 4 numbers. The second one should compute the mean of these 4 numbers, and so on down the line. Once you type in that formula and kind of drag it down and populate it down, when you scroll down this list, you should have a bunch of different numbers. I just put 2s in here just as placeholders so that the calculations would all run and so on. But when you put in the formula to compute these sample means, then you should have a whole bunch of different numbers in this list. And that's your empirical distribution of X bar. Then the second thing that you want to change is what A and B are. So in other words, if I had, if I had a sample of size 100, I know my first bin goes from 0 to 1%. X1, or I suppose X bar 1 would end up in there. 1 to 2, X bar 2 would end up in there. 2 to 3, X bar 3, and so on. And let's say that we were interested in a 90% confidence interval where n was 100, where I had 100 data points. Here's X bar 4, X bar 5 going. So X bar 5 covers the bin from the 4th to the 5th percentile, and X bar 6 covers the region from the 5th to the 6th percentile. So for the 90% confidence interval, I would want to choose the 5th percentile, which would be the average of X bar 5 and X bar 6. So if n was 100 and I wanted a 90% confidence interval, I would change these to be 5 and 6, and that would grab the 5th and 6th smallest numbers in this list of sample means. Now, of course, the actual n is 200 instead of 100, and the confidence interval one is 95% or 95% confidence interval. So we're looking for the 2.5 percentile and the 97.5 percentile, but it'll be a similar idea to this. So just think through how that would change things. But this should give you, the ability to work through those MyStatLab problems maybe a little bit easier with a little less hassle. And again, for those problems, you're given a certain resampling. So you're given, these 200 resamplings to use. This computes the resamplings randomly, but you could just swap in those 200 resamplings from MyStatLab and use this if you wanted to. And then this is your lower and upper bound for the confidence interval. Okay, and then the third thing that I want to do is just to come over and work through a couple of actual problems. So I'm going to just bring up preview here. And I think question 3 was the one that I wanted. Yeah. Let me close this one so that it's not using up a bunch of memory. There we go. Okay, so if we look at question 3, we have a sample of college students. The sample was of size 4, 10, 5, 2, and -4. And they give you 10 bootstrap samples. So these are 10 resamples that are given to you. So, we're imagining somebody has already done the job of doing all the random draws from the original sample with replacement. And now our job is to construct an 80% confidence interval for the mean. So I'm going to take this data. The way that I like to do this is the copy to clipboard way of doing it. I suppose you could do the open in Excel option, but if you copy to clipboard, Control C to copy it in. I don't know if it copies automatically, but I always just hit Control C here. Come over to Excel, pick a cell, and Control V will paste it. Now, one thing that's kind of annoying is you could do the work with the data this way, but I don't know why they put the data horizontally like this. That's kind of strange. I like my data being oriented vertically. That also works much better for Excel's like auto-populate options for formulas and things. So I'm actually going to copy this again with Control C. I'm going to pick another cell in this table. I'm going to right click and do paste special. So I'm going to do paste special and then paste special. And when I paste, I'm just going to click this button down here for transpose. That'll just make the columns rows and the rows columns. So that just puts the data in the orientation I want. Super nice little function to kind of know about. And there we go. So these are my 10 resamples. Now, what was my goal? My goal was to compute a confidence interval for the mean. My point estimate for the mean is X bar. So I want to compute a bunch of sample means. I do equals average of this data. And then I just double click to populate this list. Now, these aren't randomly generated. These are just numbers over here that were given to us. So we can sort this list. We'll sort by this column F, the sample means column, from smallest to largest. We want to make sure we grab all of the data, I suppose. I don't think it doesn't actually matter that much, but just, for good practice, I really should have grabbed that first column too, so that all the data is being sorted properly. And now when I sort, I see I've sorted lowest to highest sample mean, and I've kept my sample numbers with the associated sample. So just in case for some reason we cared about that, that's probably good practice. Doesn't really matter for this problem, but probably good practice to do. So here's my list of sample means. And I have 10 data points, right? 10, I have X bar 1 through X bar 10. So that tells me this guy is kind of covering the percentile bin from 0 to 10%, 10 to 20%, 20 to 30, and so on. If I want an 80% confidence interval, that means that I have 80% in the middle and 10% in each tail. So my lower bound is going to be the 10th percentile of this data set. My upper bound is going to be the 90th percentile of this data set. So I need the 10th percentile and the 90th percentile. I know the 10th percentile, this one covers from 0 to 10, this one from 10 to 20. This is going to be the average of these two numbers. And the 90th percentile similarly is going to be the average of these two. The highest one goes from 90 to 100. The next highest goes from 80 to 90. 90 is right in between the two, so we average those neighbors. We want to run to one decimal place because that's what my stat lab says. And this gives me what? 0.1 up to 8.4. So that should be my 80% confidence interval, 0.1 to 8.4. Let's check it. And now what do we want? We still want an 80% confidence interval, but for the standard deviation, for S. Well, what do I have to change? Does this change at all? No, this calculation is based on the confidence level. So I need to change my calculation to be sample standard deviations. I need to calculate the sample standard deviations. And very importantly, I need to sort again, lowest to highest. It's the standard deviations aren't going to automatically be sorted the same way as the means. So here I need sample standard deviation of the data. Let me populate that down. And again, very important that I sort this list again, because we can see it's not sorted now. So these numbers over here are going to be wrong right now. But if I just sort again, it remembers how I sorted before. And here's my 10th and 90th percentile, my upper and lower bound for the standard deviation, for the confidence interval standard deviation. Looks like it should be 2 and 6.3. Now let's look at question 4. Question 4 is very similar. The difference is in the number of Bootstrap resamples. Here we have 200 instead of just 10. The data can just be a little more unwieldy. We just have to be a little more careful when we're doing some of the Excel import and so on. So here's my data. I'm going to, again, click my little copy table option and copy to clipboard. Control C. I'll open up a new sheet. And I'll Control V. And I don't want to have to scroll over and select this all again, so I'm just going to Control C again to copy it back into clipboard. I need to paste it into Excel once so that so Excel picks up the formatting, and then copy it back into clipboard with Excel's formatting, and then do the paste special. I don't think I can do the paste special right off the bat. So I've copied it again. Now I can click down here, right click, paste special, and paste special, transpose, and OK. And you can see we have this similar setup now. And this is, oh, I closed the spreadsheet, but this would be the setup that you would work off of, these samples. You would put that data in here. And then once you put in the formulas for the sample means and change these numbers to what they ought to be, this will give you the answer for the lower and upper bound over here. Just make sure to do things like rounding to 1 decimal place and so on. Note that for this setup, you don't have to sort because I use this small function. So you don't need to sort the data. You don't need to paste the data in and then sort the whole table based on the mean or standard deviation or whatever it is you're computing. So these Excel spreadsheets will be in, or this one in the demos one will be on Blackboard. So you can take a look there if you want to download these and use them as a resource. Yeah, and I think that's a pretty good overview of bootstrapping, what it is, and then how to work with the data in Excel.